This series of interlocking shapes is a new kind of material.
What we created is a new fabric.
Designed on a computer and 3D printed.
Very much inspired by the medieval chainmail.
With some amazing properties.
Which can be tuned from being soft and foldable to being stiff and rigid.
Chiara Duraio and her team had a very specific idea for a new kind of smart fabric.
We really wanted to make a material that can change stiffness on command. And we were thinking about solutions, for example, for wearable medical devices. Think about, for example, supports or exoskeletons that when needed, they could become rigid like a cast to provide support or protection to the wearer.
And for inspiration, they turned to coffee.
If you think about coffee grains, when they are unpacked and loose coffee grains, they can be poured like a liquid. However, coffee grains, when you buy them, sometimes they are vacuum packed. And when they're packed, they're really stiff and rigid, like a brick.
This change in properties is a kind of phase transition, from flexible or flowing to stiff and rigid. And it happens when the individual particles jam together. How stiff the final material is depends on the shapes of the particles and how much they can touch each other.
When you have 2 grains of coffee, they can only touch at one point. So that's a single point of contact. And this is the classical example of convex shapes. They can only touch at a point. However, if one of the particles, for example, is concave, like a crescent moon, then you can imagine that 2 adjacent particles could interpenetrate more tightly or fit more snugly with one another. Think about pieces of a puzzle.
Chiara's team designed a series of complex 3D particles that could be made to interlock, connecting at multiple points. The idea is that the more contact there is between them, the more solidly they can jam together. When compressed in a vacuum bag, the material becomes stiff enough to support over 1 kilogram of weight. The precise properties of this kind of material could be tailored to specific applications.
We could replace these materials with other, for example, stiffer materials like aluminum or steel. And you could also think about making these particles much larger for deployable architectural structures like emergency bridges or shelters.
Though vacuum packing might not always be the most practical way of changing the fabric's properties.
We are, for example, exploring alternative solutions for compressing or jamming particles that include external fields like magnetic attraction between adjacent particles or tension created by fibers and pulleys that could be interwoven in the hollow space within the particles. Those actuated either by a small motor or, for example, in response to external stimuli like temperature, pH, or light.
There's a long way to go, but this smart fabric could be the next link in the chain towards tunable materials.